Hello, so today I will be going over summative problem 7. So the problems we're trying to solve are, number 1, compare the magnitude of the spin angular momentum and the orbital angular momentum of an electron in the 3D orbital of an H atom. Number 2, write down the Slater determinant wave function for the ground state of the Be2+ cation and show that interchanging the labels of the electrons is equivalent to changing the sign of the wave function. Number 3, what are the values of the total angular momentum quantum number J may occur for atoms with the terms below, and how many states with different values of Mj belong to each level? So, what we're trying to gain from these problems in number 1, we're trying to find spin and orbital angular momentum. Number 2, we're trying to show how the Slater determinant, if you switch the labels of the electrons, is equivalent to changing the sign. And we're going to look at angular momentum quantum number J and atomic term symbols for number 3. So our problem-solving approach for number 1, I'm going to use formulas from our notes, knowledge of values for L, and a ratio to answer this problem. For number 2, we will be drawing out a Slater determinant, interchanging the labels, and solving to show that this will change the sign of the wave function. And 3, we will use our knowledge of atomic term symbols to solve this problem. Okay. So we're going to start with number 1. So we're going to be comparing the magnitude of the spin angular momentum and the orbital angular momentum of an electron in the 3D orbital of an H atom. So what I like to use for these problems is a little chart that we got from class. Just shows the SP and D and then N equals 3, 2, 1. It's just helpful to remember those values. So first we're going to start, so we have the spin angular momentum and the angular momentum. First we will start with the spin angular momentum. Alright, and we have an equation for that. It's going to be absolute value S equals h bar root s plus 1, and our value for s is always going to be 1/2 regardless of if our electron is spin up or spin down. Alright, so we have our equation. If we solve this, we're going to do absolute value of the spin angular momentum equals h bar square root 1/2 times 1/2 plus 1. This is going to end up equaling h bar times root 3 over 4, which can simplify down to h bar root 3 over 2. The next thing we're going to go for, the problem asks for our orbital angular momentum. So we also have an equation for that. It's going to be the absolute value of the orbital angular momentum equals h bar square root L times L plus 1. So since this is a 3D orbital of an H atom, we can see that our D orbital here has an L value of 2. So we're going to want to sub in that value. Absolute value of L equals h bar root 2 times 2 plus 1. That gives us h bar root 6. And now we have both our values for the spin angular momentum and the orbital angular momentum. The way we can compare these, as the question asks, is with a ratio. So we can take S over L, which was h bar root 3 over 2 over h bar root 6, and we will get 1 over 2 root 2, which is equal to about 0.35. So the orbital angular momentum exceeds the spin angular momentum by a little less than a factor of 3. Alright, so now we're going to address problem number 2, which states, write down the Slater determinant wave function for the ground state of beryllium 2+ cation and show that interchanging the labels of the electrons is equivalent to changing the sign of the wave function. Alright, so what we do know is that our beryllium 2+ cation has 2 electrons. In the 1s orbital. Alright, so because we have 2 electrons, they should be spin paired, so we're going to have 1 alpha electron and 1 beta electron. Alright, so we know that the way to write a wave function for a system to make sure it obeys the Pauli principle and the indistinguishability of electrons is a Slater determinant. So first we can write a Slater determinant for this problem. We will have psi 1, 2 equals 1 over the root 2. That's just our normalization constant. And then we will begin our Slater determinant. So psi 1s 1 alpha 1. Psi 1s 2 alpha 2. Then we'll have psi 1s 1 beta 1 and psi 1s 2 beta 2. Alright, so now what the problem asks us to do is show that we can interchange the labels to then make it equivalent to changing the sign of the wave function. So now we're going to make a new Slater determinant where we are going to interchange the labels of electrons 1 and 2 to show that the sign of the wave function changes. So we will start by writing 2, 1 here because we're interchanging labels. The same normalization constant. We'll have psi 1s 2 alpha 2 psi 1s 1 alpha 1. Then we'll have psi 1s2 beta 2 and psi 1s 1 beta 1. Alright, so we can simplify that down to 1 over root 2 psi 1s1 psi 1s2 times alpha 2 beta 1 minus alpha 1 beta 2. And even further, we can go 1 over root 2 psi 1s 1 psi 1s 2 times, like this, negative alpha 1 beta 2 minus alpha 2 beta 1. Alright, so what we're going to want to do next is move that negative sign out to the front. So we'll have negative 1 over root 2 psi 1s1 psi 1s2 times alpha 1 beta 2 minus alpha 2 beta 1. Alright, so what we can do with this is turn it back into a Slater determinant. So we will have our negative 1 over root 2 up top, and we get the Slater determinant psi 1s1 alpha 1 psi 1s1 beta 1 psi 1s2 alpha 2 and psi 1s2 beta 2. And now you can see that these two wave functions are exactly the same. However, the signs are swapped. So we have a negative sign up here. There's no negative sign there. So what we end up with is the negative of the wave function 1, 2. Alright, so now we're moving on to question number 3, which states, what values of the total angular momentum quantum number J may occur for atoms with the terms below, and how many states belong to each level? We have 1s, 2p, and 3p. So, just to recap, so atomic term symbols, the way they work is we have this big L value that remains as a letter. We're going to have a J value at the bottom, and then 2s plus 1 right up here. This is called our multiplicity. Alright, and again, the L is going to represent the total orbital angular momentum quantum number. S is our total spin angular momentum quantum number. And J is the total angular momentum quantum number. We also know that J equals L plus S. It can range from L plus S down to the absolute value of L minus S with any integer value in between. So, we're going to get started with our A, which is 1s. Alright, so the S symbol here, remember up here, it tells us that our L equals 0. And we can look at our multiplicity to find our S value. So we know 2s plus 1 is going to equal 1. So our S value for this one is also 0. Now, what we're trying to solve for is J, which is going to go right here. So we know that J can equal L plus S down to the absolute value of L minus S. But in this case, both of our values are 0. Our J value is going to be 0. So our only term symbol that we can have for A is 1s, 0. Alright, now we can move on to B, which is 2p. Alright, again, the P tells us that our L is going to be 1 right up here. So our L is 1, and our multiplicity can help us find our S again. 2s plus 1 is going to equal 2 this time. So our S value is going to be 1/2. So the possible values of J again range from L plus S to L minus S. So our L plus S is going to be 3/2. Our L minus S is going to be 1/2. Now also would be any integer value in between 3/2 and 1/2, but those are the only values here. So we're going to have 2p 3/2 or 2p 1/2. We have 2 atomic term symbols that we can have for this problem. Finally, we can move on to C, which is going to be 3p. Again, the P symbol here tells us that our L is going to be 1. So we have L equals 1 again, and our multiplicity, 2s plus 1, in this case, is going to equal 3. So our S value is going to be 1. So what we're going to do, again, is J equals L plus S, 2. And our J can also equal L minus S, which is going to be 0. So these two J values have an integer value in between them, which is the number 1. So we can have 3 atomic term symbols here. 3p2, 3p1, and 3p0. Alright, so now I'm just going to quickly go over each of these problems one more time just to close the loop on our summative problem 7 here. So in this problem, we calculated a spin angular momentum and an orbital angular momentum. The spin angular momentum is always going to be this value because s is always 1/2. For the orbital angular momentum, it depends on what shell up here your electron is going to be in. In this case, we had an electron in the 3d orbital of an H atom, so our L was 2. The value we got was h bar root 6, and we did a ratio to compare those two. Alright, number 2, we showed how changing the labels on Slater determinant ends up giving us the negative of the original wave function. So here we came out with a negative value up in front, and there's no negative sign right there. So we just ended up with the same Slater determinant, but a negative in the front of this one. So that shows us that our wave function is negative when you switch the labels of two electrons, and that also helps us make sure that this satisfies the Pauli principle. Finally, we looked at our atomic term symbols. We used our chart again here, our knowledge of atomic term symbols here. We came up with one answer here, 2 different atomic term symbols here, and 3 down here. Alright, I just wanted to say thank you for listening. Today we learned about spin and orbital angular momentum and how they can differ, Slater determinants and how interchanging labels changes sign of the wave function, and how to understand atomic term symbols. Thank you.